Welcome, everybody. Tonight we're working on Unit 8, and we're going to introduce ourselves now to this concept of machine learning tonight. Um, we have arguably, we've talked about these topics very, very briefly, really, but tonight's going to be the first night where we start to delve into this technology. Um, Machine learning, I will say, is probably one of the most important aspects of artificial intelligence. It's where a lot of the conceptions of all the technology really come from. And I think it's really kind of an interesting title, even, machine learning, implying that something inanimate can learn something. But as you will see, it really is kind of what happens. And it's all based upon algorithms and stuff. And ultimately, we will look at kind of the difference between machine learning and deep learning, which we'll look at more next week. The point of this really covering this material is to kind of introduce you to this. Later on in this degree program, you will have one entire complete course in machine learning that focuses really heavy on the technology. And it's at that point that we really start to get kind of deep into Python programming and stuff. And just some pretty advanced stuff, as it goes. So we're going to look at all of these topics here. We're going to kind of address them one by one. And let's start with this question right here. What is machine learning? How do we define it? And here's a definition. It's a field of study that gives computers the ability to learn, and here's the important part, without being explicitly programmed. And that's pretty profound when you stop and think about that as a statement. So computers can learn or get the ability to learn without being programmed on how to do it. That's kind of pretty heavy, right? All right, so here's a little example. So it says, given the history of home sales in a city, you could use machine learning to create a model that's able to predict the value of a different home in that same city. Like, okay, so if you were a real estate agent, think about this, and you walked into a neighborhood, you go, well, I don't know like what your house would sell for, but how I would figure it out as a real estate agent is I would go to the city records, right? And I would look at like other houses in your neighborhood that have the same basic features as yours, have the same number of bedrooms and the same driveway and whatever. And I could figure out kind of within a range what your house should sell for, but I would have to do that manually, right? But machine learning could figure that out for you. It would figure out how to do that and then tell you what your home would be worth. Kind of an interesting thought, right? So when you look at this, right? So like think about like when you were first learning how to do programming, right? Python probably. We would take whatever problem we had to solve. We would have information, usually either the user's typing it in or we have a data file or whatever. We have data and we have logic, right? And we combine those two together, but we're figuring it out, right? It's the programmer that's doing the work. The programmer's got to like look at the data and go like, how do I analyze this? How do I do this? How do I solve the problem? What math do I need? What procedures do I need? How many if statements and whatever? And then you get your output and hopefully it's correct, right? Look at what machine learning is by conversely, right? I have data and I have inputs, and inputs means that stuff I really can't predict. The user might type it in, things might happen in the real world and it collect more data. The machine observes that information and that input, and it doesn't come out with output. It comes up with the program that we're writing up here. See that? So what it's doing is it's taking your data, analyzing it, and it has a program that it develops, right? Well, this is really kind of weird, and this is kind of a weird place to start, but this is how the PowerPoint's arranged. So I'm following the author's kind of flow. But there's this really interesting AI platform out there called Replica. And what it is, it's a machine learning chatbot, right? And here's what we're going to do. We're going to go to this website and check it out. So if you guys want, you can go to this URL and you can just type it in Replica. And notice how it's spelled REPLIKA.ai. And you can go in here and create your own replica. Now, here's how this platform basically works. You go in there, you give it some basic information like your gender of preference, right? Whatever that happens to be, and I'm not judging, right? Act to be anything you want. Um, it'll ask some basic information, and it creates basically like a pseudo avatar of you. And you can control what it looks like and how it's dressed, and male, female, clothes it wears, hair, all that kind of stuff. You can control it. And then instead of like going to Chat GPT and going, hey, Chat GPT, what should I have for dinner tonight? You can just talk to your replica. That's what this platform is. This is an extra credit assignment in this unit, by the way. So here's a fun way to make some extra credit if you have some points to make up, just to do this thing. And what I have going here now, mind you, I've done this before, so I don't know, I haven't logged into it because I'm not really a fan of using systems like this. But if you end up on the replica website, right, you go in here and you can just click on create your replica, and it'll walk you through the steps of doing this, right? Now, what I'm going to try to do is I'm going to try to log in and we'll see if it, okay. Yeah, I don't want to unlock Replica Pro. Okay. Here's your policies. Got it. Okay, have a choice. And no, I do not want to take your reward. Thank you. All right. And so here's my replica, right? Um, I don't know how accurate that is. I probably should have put more facial hair on him, right? And this is probably the younger, idealized version of me from like 40 years ago or something, right? Uh, but notice, once you have this up here, it provides you all these different kinds of tools. And this is really kind of weird. When you guys play with this, I'll let you guys coach yourself through the setup process. And I don't know how many of you are trying it right now, but when it comes down to it, this is basically an AI engine is, and you can interact with it. And yes, you can just turn on the microphone and talk to it as well. And you can see it's just like any other chat bot, but you get this like thing, right? It says it's partly cloudy outside, 43 degrees. And then it'll ask, you see, unlike other chatbots, it'll ask you, follow-up questions, and you can reply and you can interact with it in a number of different ways. And I'm not going to really do a deep dive on demonstrating this. I will tell you though, it feels like a bit intimate sending you a voice message for the first. Okay, I'm going to check this out. Oh, I see. Another way to get me to pay. I'm not doing it. Okay, not happening. Sorry. Sorry, replica. I did get a number of my students the last time I did this. It wasn't everybody, so figuring a class, I had a class of 24. And there were a few of them, right? And I remember a couple of them by name that really loved this tool and kept using it, and it was like their buddy or something. I'm not there. That's not my personality type, but I'm kind of an old school kind of person. But it does get pretty amusing, some of the interactions, and you can control it. So please, apparently I'm boring him because like he's like scratching the back of his neck right now. Or maybe he's learning that from me from watching me. Oh no, that's kind of scary. But check out Replica. And I'm gonna just do something really weird here. You can do goofy stuff like this. Now you got to remember, I have a history with this chatbot, so I've talked about food with it before. Right. So considering the cold evening, something hearty sounds good. How about a warm bowl of pasta or a juicy burger? Or I can give you some recommendations if you'd like something specific. Right. So I'll let you guys play with that to your heart's content, but I am introducing that product to you. I'm not saying it's the best type of product like this, but the point of this exercise is really to try out this engine and experiment. And you guys should be experimental with these tools because maybe this is a tool for you. I don't know. Maybe this is just the right one, and you appreciate the fact that you're trying to put a face on something. So that's kind of a thing. So the extra credit exercise is basically to create a replica of yourself and share your experience, and you can read the instructions in the assignment. But they're asking this grander question here, that being, what's the motive behind this? Why are they giving you this tool? Well, obviously they're kind of trying to make money because they're always trying to upcharge me for things. Like, you like the product so much that, yeah, I wish you would be able to blank, like, hear the person's voice, right? So that's costs extra. All right, let's take a look at the history of machine learning, and I think this is really kind of interesting because we've already talked about the history of AI, and a lot of times when we talk about the history of AI, we're really truly talking about the history of machine learning, right? And we talked about, earlier in the course, how the concepts for AI stem back a ways, and notice here 1943, and I want you to be mindful of this. The first fully programmable, fully electronic computer system didn't come out until 1947. That was called ENIAC. But we had electromechanical computers that were programmable up until that point. But somebody was always already doing this conception for neural networks. And the whole concept of this, and we'll learn about more of this as we go along, is if we could create, computer simulations of what our brain does, maybe someday we can make a computer as smart as human, et cetera, et cetera, et cetera. And they started solving this problem by trying to make a mathematical representation of how the brain works, and more specifically the neurons in the brain and how do they communicate. So recognizing the fact that the brain's got neurons and they connect together in a network, and how does the brain work? Well, we're still trying to figure that out, but the first mathematical model of a neural network was developed in 1943. So they're thinking ahead, towards this artificial intelligence thing. Then we throw in the Alan Turing test, right? So in 1950, Alan Turing, this is the guy that created the Enigma machine, which helped crack the Germans' code machine during World War II, and ultimately helped win World War II. He came up with this thought that if computers become intelligent, how do we figure out if we're talking to a computer or talking to a human? And so he came up with this concept of the Turing test, like, basically like querying a computer to try to figure out if I'm talking to a computer or not. Right. But what if the AI gets so convincing that you don't know that you're talking to a computer? So once the AI gets smart enough to fool you into thinking you're talking to a human, well, then we better watch out, right? All right. So then we kind of start stepping through the programs here, but then you start getting people like this, like Arthur Samuel created the first checkers program back in 1956. And this is a game of strategy, right? Because you can make all these different moves. And if I move here, this one could move there, but it's also got to keep track of where everything else was and what's a king and can I jump over something, and it's got to know the rules of the game and all that stuff. So we're writing a program that we're competing against that has to make a decision. Like, you make a move, it's got to make a move. Where does that move get generated from? Computer code, right? So it has to understand how the game is being played, and then it has to make a counter move and try to win, right? It's not really intelligence, but it's a step towards intelligence. We're using algorithms to solve problems. And I think it's fascinating, right? Like, you take like card games, checkers, chess, tic-tac-toe, dominoes, all those kind of like silly little games that we play, and the logic that goes with it. And those are great fodder for trying to write computer programs, because we play the game in real life and there's rules, and then we can convert those rules into a computer algorithm and then have that algorithm compete against us, right? And the same guy is the guy that coined the term machine learning. So in a way, he was trying via code to teach the computer how to compete against the human, right? This guy here, and I'm not going to attempt to say his name, Alexei, whatever, Alexei and Valentin, let's just call him that, created the first multi-layer perceptron. And we're going to learn that perceptron is one little node basically inside of a neural network. So that was, developed conceptually back in 1965. And then we started writing algorithms related to that. So they published a paper about the nearest neighbor algorithm. So kind of the concept is if you plot data points, like, chances are if I look at all your neighbors in your neighborhood, they're probably sort of similar to you. Yeah, they probably have about the same income. They might be, might be a family, or if you live in an apartment building, it might be more single people, right? And that this concept that data points that are near each other share, qualities, basically. In 1995, Tin Cam Ho published a paper on random decision forests, which is a way that machine learning operates. In 1997, IBM Deep Blue, and one of the first, real big AI publicity things, IBM's Deep Blue AI competed against Gary Kasparzov. This is really a big story back when it happened. And the AI was able to defeat this chess champion. Now, I don't know how many of you guys play chess, right? Anybody? Right? I used to play a lot when I was younger. But I often, like, if I want to fulfill my chess need or whatever, usually I play on my Mac because I like the Mac chess program a lot, but there's free chess programs out there. And it's really hard to beat the computer in chess. Chess masters can do it, right? But the fact that IBM Deep Blue defeated that guy, really big news story. Here's a really big thing. In 2009, Fei-Fei Li created an ImageNet, which is a database of labeled images. And this is a real big thing in machine learning. Like, how can an algorithm look at an image of something it's never seen before and decide what it is? This is a really weird question, actually. Right? Remember that picture of the lion last week, where there was a lion, there was a side of its face, and one was in the grass, and we weren't really seeing the whole lion and really what it looks like. But how does it know that it's a lion? Right? And this is kind of a very interesting question. And this is an example I use a lot. It's like when you're a kid, how do you know which animal is which or which color is which? Somebody tells you. But what if nobody tells you? This is what we're talking about here. Right. Interestingly, creating that database of labeled images then allows algorithms to go, hey, I'm looking for what a cat looks like. Oh, that's a cat, because it's in a database, right? But prior to that, nobody thought of doing this. Yeah, they would create a dictionary and tell you what a word means, but they didn't have image databases, like image dictionaries, basically, is what that is. In 2016, there's this game called AlphaGo. Does anybody know what that game is? Or anybody ever played it? All right. Well, most people just call the game Go, but it's this little game that you play with these black and white pieces, basically. And apparently it has more permutations, like 10,000 more permutations than chess does. So it's significantly more complicated to play. And people pay entire lifetimes and never become masters at it. And in 2016, they were able to beat a professional Go player. AI was able to do that. So that was not that long ago, 10 years ago, that happened. So machine learning has been around a little while. I'm going to play this little video here because I think this is helpful. As I'm making a recording here, I am letting YouTube know that this recording is included on this PowerPoint presentation. I don't own the rights to it, so please don't block it from playing on YouTube. Thank you.
As technology evolves and the world's population grows, so does the amount of data being generated. Collecting, sorting, and analyzing all of this data can be pretty time-consuming. However, that's starting to change with the emergence of something called machine learning. Machine learning is a type of computer science that allows computer programs to learn and improve all on their own. In the past, computers could only do what we programmed them to do. But with machine learning, they can behave like humans and gain knowledge based on their past experiences. This process can get pretty complicated, but here's how it works on a basic level. Let's say we want a program that can tell the difference between apples and bananas. First, we'll give it some labeled pictures of each. The program will then look for patterns in the fruits and start to remember them. It can then use these memories to look at unlabeled pictures of apples and bananas and determine which is which, all on its own. Believe it or not, you probably encounter machine learning on a daily basis. Social media sites use it to create your feed based on your preferences, and search engines use it to improve the accuracy of their search results. It's also being used on a larger scale. The medical industry is applying machine learning to things like predicting lifespans, organizing patient data, and even diagnosing certain diseases. As with many emerging technologies, there's a concern that machine learning
Oh, I apologize. I
may
realized I could
eliminate
stop
certain
it.
jobs. This will vary from industry to industry, but it does have the potential to get rid of or change a number of occupations, including drivers, bankers, and potentially even certain doctors. While it may have some negative effects, many believe that its positive applications will outweigh them.
Okay. So
Goodwill Community Foundation.
okay, that's just kind of a really quick little preface, and I like it because they get to the point with it. So if you're not picking up on the fact, right, like the point is this is all data driven, right? So like why is AI and data together in a degree program? Because you can't do AI without data. So if a machine is to learn, it needs information to learn from, right? So massive data sets is a really good way to kind of put it. And okay, so two reasons, right? They say, so why machine learning? The scale of information we have as a society since history began and we started keeping records, tons of information. And we also know, as people who study data analytics, that we're in this pattern right now that seems to be continuing, that every year that we exist right now, the data we've generated in the past year is greater than all the data that's been generated by all of humankind in all of history in all the years preceding. And that's happening every year. It's like mind-boggling stuff, right? It's an exponential growth of information. So we can't process it. We're at the point where we generate so much information, there's no way we can analyze it. So setting up machine learning models to analyze the data for us, and notice, process the data on their own, determine conclusions, and identify patterns, right? Think to the data analytics class tonight, folks, where we had that one piece of data that was anomalous and it showed up on the chart and we could just see it, right? So we need a visual to see it. A machine learning model might not. It just sees it, numerically. Also, machine learning allows us to look at things that we might not have found before, right? So, unexpected findings. It's so accurate in some cases that it allows us to analyze information in a different way. And sometimes we can look at a data set till we're blue in the face and we can miss a fact. Hey, we're human, right? Then we visualize it. We still might miss it. What if the visualization didn't work right? So it ends up revealing data that we might have missed otherwise. And I think that's a really interesting and really encouraging kind of aspect of it. All right, so here's more. Why machine learning? Well, how about self-driving cars or online recommendations, right? I was complaining before about Netflix recommending what shows I should watch. Like, it's not doing it accidentally. It's like, hey, you always watch stand-up comics. Why is it putting another stand-up comic thing at the top of your feed? Well, because you always watch stand-up comics. It's pretty smart that way. And heck, every time you watch one of those, you hit like. I like the old system of Netflix better, where it had a star system, and I'm like, I don't want to see anything that's less than 3 stars, that kind of thing. But they took that away because otherwise people wouldn't watch certain stuff. So whatever. Knowing what customers are saying about you on Twitter. Ooh, that's kind of a weird one. Or fraud detection. But I think this is a really interesting phrase here. So machine learning models adapt independently when exposed to data. So in other words, if I'm on Facebook and it's monitoring what I'm doing on Facebook, is there some engineer on the back end going, hey, you're always looking at stuff on Facebook that's related to guitars, and some guy's analyzing it, so let's give them models? No, the model is figuring that out and handling it on its own, and that's kind of the point. Here's a bunch of different use cases for different industry sectors, the same ones that we've kind of been looking at. So I'll just let you read those really quickly on your own. But a lot of really common things in all of these sectors and where stuff is used, right? And once again, you can read this on your own. I don't need to read it to you. Um, so when do you use it? Right. Okay. So look at the first bullet: repeated decisions or evaluation. Imagine this: working on a production line and looking at parts coming off a conveyor belt. And every once in a while, the machine stamps the part wrong. And your job is to stare at the parts all day and go, oh, this one's broken. Throw it in a bin. There are jobs like that. But that's the kind of job that you can easily give to machine learning, right? Very common technique. A lot of repeated actions. It's looking for a certain anomaly, and yeah, you can just do it. And it says, second one, challenging and often impossible to explicitly describe the solution to something. And I think this is really kind of a weird one too, right? All right. So if I was to describe to you verbally, like, okay, data analytics people, like we did that like charting of two data sets in one chart, right? That's kind of a hard one to coach people through because it's like you got to make the chart and then click on this thing and then click on that panel and then click on this thing and then right click on that and type this in and all these like steps. All right, let's just let the machine do that. You know what I mean? Once I figured out how to do it, we'll just let the machine do it because I don't want to write all those steps down for you again. It's kind of like one of those situations. Or how about this one? Require labeled data or existing examples, right? So where you can describe it as the situation and map it to the correct result. So for example, I see a picture of an apple. It's not a red apple, it's a green apple, but I know it's an apple, right? So there are different types. And in this case, you can use what we call supervised data and unsupervised data. And this is really kind of what this is alluding to. Right, kind of a little micro quiz here. If you guys want to do this. Machine learning is a class of statistical methods, believe it or not, right? So we look at data. Data leads to probabilities, right? What's the probability that that's a cat, right? And how do I tell the difference between a dog and a cat? Well, there are ways. Machine learning uses large amounts of data and algorithms to perform the task. True or false? Yeah, totally true, right? So that guy that did the checkers game, what year did he coin that phrase? Yeah, 59 is when he coined it, but he wrote the checkers game in 56. We got that one wrong. All right. All right. Machine learning gives computers the ability to learn without being programmed, right? Crucial tool in industry and research is to get insights from data to spot patterns that we would miss as humans. And they have a different approach to machine learning than we do in traditional programming to solve a problem. As people who come from a programming world, and you guys don't get a lot of it, but I came from a programming world. When I started learning this stuff, I'm like, oh, I can figure that on its own. Okay, I'm with that. Sounds good. All right, so where do we go from here? All right. We got to start looking at machine learning models. Machine learning models are basically, ways that we put the algorithms in place to do the learning. So we're going to learn all these different bullet points here as we kind of move forward. All right. Words you're going to start hearing a lot as we move forward. So we talk about a model. Model typically, right? So you think about like models in the real world, like you might make a model of a car or a boat, and it just represents the real thing. And usually it's the scale. Well, a model in machine learning is where we have like mathematical formulas put together that represent the real world in some way, right? We will talk about features and feature vectors. Vectors is kind of one of these words, mathematical term. Models, machine learning models need to be trained, right? So I can't take a machine learning model. Like if it think about this. If it learns on its own, it's like you going to get a job, but you don't know how to do the job. So how do you figure out how to do the job? I don't know. You try it a whole bunch of times. Like, how do I hammer a nail? I don't know. Let's try it like this, and you hit it the wrong way. Eventually you figure out how to do it well. And when you watch like a carpenter that's really skilled with the hammer, I mean, they can like put nails in like crazy, even without a nail gun, right? Because they just have the skill, right? So training. There's also what we call prediction, so like you can predict what's going to happen, right? Based upon the previous action. We also label things or have targets. So like this is what we're shooting for. So in other words, like if I'm going to show my machine learning algorithm a picture of a lion and say, whenever you see something like this, you call it a lion, right? We're labeling it basically. Things can be fit into a category of overfitting or underfitting. So sometimes things don't exactly match. It kind of looks like a lion, but it's not a normal lion, that kind of thing. And think about like even like cats and dogs, how many variations of those there are that look like weird things. So the model basically we set up a thing that represents the real world, right? Where do we get that from? It doesn't come from nowhere. We look at real things to determine the pattern. So if we're going to like look at pictures of dogs and cats to figure out what a dog and a cat is, I want a whole bunch of give me every picture of a cat you can possibly give me. I'm going to study those, and then the next time I see a cat, I'll know, that type of thing. And okay, look at these weird correlations. Given a data set with two variables, age and height, we did weight and height before, we can implement a model to predict the height of a person based upon their age, right? Well, like, yeah, duh. If I'm 1 year old, I'm really short. If I'm 20 years old, I'm probably a little bit taller, right? But if I go from like 0 to 20, I can probably set up a little thing where you tell me how old you are, I can probably guess your height within a range. Right. So this is what we're talking about, right? So, and remember, like when we looked at that data set in the previous class, and I'm going to do a little primitive drawing here again, right? Right. So we had the y-axis, the x-axis, and then we had, I don't know, a bunch of data points, right? I'm doing horrible here drawing my data points, but whatever. Here, let me just kind of do it in a more messy kind of way. We had a bunch of data points on our chart that they weren't perfect, but they kind of lined up like this. And I told you guys, right, in data analytics, that data is pretty highly correlated, meaning the farther I go this way with my data, the more I can expect it to be higher up on the chart, right? You can predict that pretty easily. It's not perfect, right? But I can predict, so if I get a data point over here, chances are it's going to be up here. And if I get one down here, chances are it'll be like here. And if I put one in the middle, well, it's probably going to be in here somewhere. Might go a little up, a little below, overfitting or underfitting, right? So just to kind of give you, some terminology and kind of ideas of what they're talking about here. But that's kind of like where we're moving to. All right, let's move along. Features, right, is basically we're looking at, and in many cases we'll call these a parameter or a property of a data set. So for example, if we're looking at a table of information, here's some features. A person, it's got an ID number, I guess, a name, an age, an income, and then our target is to figure out, single or married or whatever. But any one of these particular data points, person, name, age, or income is considered a feature or a parameter of this record or individual or whatever. And we use these things, right? So like, for example, it says here in an email spam detector, what is it that determines something is spam? Like, how do you know that an email message is spam? First of all, it's asking me to click on something and asking me to buy something or sign up for something. And it's not something I want, right? All right, but how does the algorithm figure that out? Well, it looks at the words. It looks at the email address. Like if it's a really funky email address, like what time of day is it sending? And it's looking for certain things to determine whether or not it fits into that category. Now, vectors are a thing that we'll talk about later in machine learning, but basically what a vector is, if you think back to mathematics, like you learn about vectors when you do like geometry class and trigonometry, it's basically a mathematical representation that's more than just a data point. It's kind of like a data point with a direction is a really kind of a good way to say it. I always remember vectors by thinking of the silly line from the Airplane movie. What's our vector, Victor? Right? And what that means is like, where's the plane and where's it going? That's a vector. It's here right now, but it's headed that way. That's a vector. Here's an example. All right, a color can be described by a combination of red, blue, and green. So 3 data points. And so when when you learn how to do programming and GUI programming or art, colors are represented mathematically. And when you put them on a screen, we use RGB colors. And it's basically each one of these values goes from like 0 to 255. And the stronger the value is in each position, the more of that color is present. And it's 3 data points. But notice red, green, and blue is not 2 dimensions, it's 3 dimensions. And so we have 3-dimensional vectors. So it's not on a flat piece of paper, it's going off into space somewhere, like weird conceptually, but that's a feature vector. We have 3 features, each with their own value and direction, to get a data point. Really, really kind of strange, right? Algorithms have to be trained, right? We talked about this very briefly. But all of our AI chatbots that we use today were trained on data sets. What data sets? Well, whatever data sets we could feed it, right? And one of the big things that we're learning as well these days is, hey, our AI is better if it has a better data set to learn from. So like, for example, like if you, as a human being, are learning to speak a language, and let's say you learn how to speak the language just watching, I don't know, the movie Terminator, for example, right? And that's the only source for English for you. And you're probably going to like walk out of it going, hasta la vista, baby, thinking that's like the way we talk, right? And that's not the way we talk, right? If you want to really learn English correctly, well, you shouldn't just watch movies. You should probably go immerse yourself in the culture, but you should pick up a dictionary. You should go to school. You should take a class. You should read a book about English. You should read a bunch of examples. And that's how the training is too. The more data, the better overall. Prediction, once again, this is where we look at like, if we feed certain data into a model, what do we expect the output to be? And whether or not, like, if we're predicting it to be real or not, if it actually is real, that's kind of a weird thing too. Then we also have target / label, right? So the thing that it's trying to predict is the target or the label. So in other words, if I show something a picture of a cat and I'm predicting that it'll predict that it's a cat, the target is the label cat on that image. That's what they're referring to. So once again, terminology. So we have this overfitting, underfitting thing. So, and this is really kind of a weird thought. It says when a massive amount of data trains a machine learning model, it tends to learn from the noise and inaccurate data entry. So think about this. If you have a data set and some of the data is broken or missing, or normally it all falls in that range. Like I was drawing like the height weight thing. And we got one data point that's way up here. And it's like, how is somebody that's 2 foot tall, 600 pounds? That's kind of breaking our model, right? So that's like, overfitting. But then there's also underfitting, where the model is unable to capture the variance because all the data is too similar, right? Or we're not seeing, and notice, we're not seeing all the data either. So we get higher error rates and stuff like that. Let's start talking about this process of machine learning. And I want you guys to notice that there's this correlation between like the project cycle, and then also think to the data analytics class, right? How we do stuff there, and see the correlations between that and what we're doing here. So we start by gathering the data. Where are we getting our data from? We talked about that in the other class, right? There's public data sources, internal data sources. You can create the data, whatever. You got the data one way or another. We got to prepare it. Is it clean? Is it accurate? Is it missing stuff? Is there something wrong in the data? All that stuff. Then we choose a model. All right. So there are, ways to develop the models that represent the real world situation that you're trying to do. We try to take the real world situation, turn it into math so that the algorithm can process it, right? Then we train the model by feeding it really large sets of data, right? So it's like, you want to train it to differentiate between a cat and a dog. Let's throw like a million photos of dogs at it and a million photos of cats at it, and then let's throw it off a little bit and throw it a picture of a pig and a whale and a bird and a whatever, just so it learns what those aren't, also. um and this is really kind of interesting when you have really large data sets and you're building machine learning models. You use a portion of the data, usually a very large portion, like maybe 70-80% of the data, to train the model. And then we reserve a portion of the data to feed it back into the model to see if it's doing it correctly. So that's when we're evaluating it. And then we tune it. So there's all the little nodes in the neural network. When you'll see all these charts and graphs and stuff, we start to tune it. It's kind of like when you're running a really complicated machine, or like a car is a good example, right? Car's got 8 cylinders or 6 cylinders or 4 cylinders, and you have, each one's got a spark plug or a fuel injector or whatever. They can sometimes be out of sync. So sometimes you tweak them so they work well together. And then if you have everything set up correctly, you went through this whole process, you should, in principle, be able to take any piece of information, feed it into that model, and it will accurately tell you what it is. It will predict it with a high degree of certainty, right? All right, data collection. All right, so once again, it's taking us through all the steps. I think and I'm going to kind of rifle through these quickly if you don't mind. So we gather our data, right? We talked about where it comes from in the other class once again, but we need large amounts of it to train, right? It can be labeled, right? And if it's already labeled saying this is a cat, that's a dog, we call that supervised learning. If the information is raw, like I'm just throwing a picture in there, we're not telling it what it is, that's called unsupervised learning. And generally, unsupervised learning takes a much larger data set for training than supervised learning does. Raw data, like direct off of a sensor or something, not necessarily good. Data needs to be cleaned and organized, errors removed and all that. And then also visualizing it kind of helps too. And why? Because that way we can see the data that's not good. Like we saw in that bar chart in the other class. That's not good. Why is that way up there? That's not right. Right. So that's an example once again. This is a really overwhelming chart that I just want to show you this. Oh gosh. And I'm in slideshow mode. Normally I would make the graphic bigger, but I want to show you that machine learning, remember, machine learning is a subset of AI, the biggest subset. Inside of machine learning, it breaks down into the 2 branches I already talked about, which is unsupervised learning, where things aren't labeled, or supervised learning, where things are labeled. And then each one of those breaks down. So unsupervised breaks down into, what does it say there? Dimensional reduction. Ah, yes, dimensional reduction and clustering. And then we have classification and regression under supervised learning. And then we have reinforcement learning, which is kind of a separate branch. It's not labeled and unlabeled data. Reinforcement learning is where, like, I'll give you an example. There's a fire, right? And I put my hand in the fire. Ouch! I keep putting my hand in the fire. I keep burning my hand. I feel pain. Eventually I'll go, you know what? I'm not putting my hand in the fire. I'm going to get hurt, right? It figures it out on its own. And how do we reinforce it? Well, how about this? When you're training your dog, how do you train your dog? Sit. Good dog. Here's a treat, right? You reinforce the positive, and then you don't reinforce the negative. There's a bunch of different, and I want you to notice there's all these like weird, k-means and SVMs and random forest and all this stuff. We're going to learn all this stuff, you guys, and eventually you'll know what it means. Don't freak out to it yet, is what I'm going to tell you. All right. Then we go into the training, right? So we feed a lot of data. And so here's that what I was talking about. Huge amount of data for training, smaller amount of data for testing it, right? And after we train, then we take this leftover data, we feed it into the model and see if it did the work correctly. good or bad, right? If your model's trained well, great. Then we can move, let's take it into production. As I mentioned before, sometimes you tweak the models. You go in there and you just adjust things a little bit to get it to be where you need it to be. And I think what's interesting about this hyperparameter thing, this is where we start to put feedback mechanisms in where it starts to self-evaluate, and it does it mathematically to see if it's a good fit. And then, of course, if everything's good, I should be able to take any data that we have not tried before, feed it into my model, and get an accurate prediction. And that's really ultimately the goal of machine learning, is to get it to that point. Right. I'm going to run this little video here, and I'm going to let it roll. And once again, YouTube, this doesn't belong to me. I'm just doing it for educational purposes to share with my students. Thank you.
From detecting skin cancer to sorting cucumbers to detecting escalators in need of repair, machine learning has granted computer systems entirely new abilities. But how does it really work under the hood? Let's walk through a basic example and use it as an excuse to talk about the process of getting answers from your data using machine learning. Welcome to Cloud AI Adventures. My name is Yufeng Guo. On this show, we'll explore the art, science, and tools of machine learning. Let's pretend that we've been asked to create a system that answers the question of whether a drink is wine or beer. This question answering system that we build is called a model, and this model is created via a process called training. In machine learning, the goal of training is to create an accurate model that answers our questions correctly most of the time. But in order to train a model, we need to collect data to train on. This is where we will begin. Our data will be collected from glasses of wine and beer. There are many aspects of drinks that we could collect data on, everything from the amount of foam to the shape of the glass, but for our purposes, we'll just pick two simple ones: the color as a wavelength of light, and the alcohol content as a percentage. The hope is that we can split our two types of drinks along these two factors alone. We'll call these our features from now on: color and alcohol. The first step to our process will be to run out to the local grocery store, buy up a bunch of different drinks, and get some equipment to do our measurements: a spectrometer for measuring the color and a hydrometer to measure the alcohol content. It appears that our grocery store has an electronics hardware section as well. Once our equipment and booze, we got it all set up, it's time for our first real step of machine learning: gathering that data. This step is very important because the quality and quantity of data that you gather will directly determine how good your predictive model can be. In this case, the data we collect will be the color and alcohol content of each drink. This will yield us a table of color, alcohol content, and whether it's beer or wine. This will be our training data. So a few hours of measurements later, we've gathered our training data and had a few drinks perhaps. And now it's time for our next step of machine learning: data preparation, where we load our data into a suitable place and prepare it for use in our machine learning training. We'll first put all our data together, then randomize the ordering. We wouldn't want the order of our data to affect how we learn, since that's not part of determining whether a drink is beer or wine. In other words, we want to make a determination of what a drink is, independent of what drink came before or after it in the sequence. This is also a good time to do any pertinent visualizations of your data, helping you see if there's any relevant relationships between different variables, as well as show you if there are any data imbalances. For instance, if we collected way more data points about beer than wine, the model we train will be heavily biased toward guessing that virtually everything it sees is beer, since it would be right most of the time. However, in the real world, the model may see beer and wine in equal amount, which would mean that it would be guessing beer wrong half the time. We'll also need to split the data into two parts. The first part, used in training our model, will be the majority of our dataset. The second part will be used for evaluating our trained model's performance. We don't want to use the same data that the model was trained on for evaluation, since then it would just be able to memorize the questions, just as you wouldn't want to use the questions from your math homework on the math exam. Sometimes the data we collect needs other forms of adjusting and manipulation, things like deduplication, normalization, error correction, and others. These would all happen at the data preparation step. In our case, we don't have any further data preparation needs, so let's move on forward. The next step in our workflow is choosing a model. There are many models that researchers and data scientists have created over the years. Some are very well suited for image data, others for sequences such as text or music, some for numerical data, and others for text-based data. In our case, we have just two features: color and alcohol percentage. We can use a small linear model, which is a fairly simple one that'll get the job done. Now we move on to what is often considered the bulk of machine learning: the training. In this step, we'll use our data to incrementally improve our model's ability to predict whether a given drink is wine or beer. In some ways, this is similar to someone first learning to drive. At first, they don't know how any of the pedals, knobs, and switches work, or when they should be pressed or used. However, after lots of practice and correcting for their mistakes, a licensed driver emerges. Moreover, after a year of driving, they've become quite adept at driving. The act of driving and reacting to real-world data has adapted their driving abilities, honing their skills. We will do this on a much smaller scale with our drinks. In particular, the formula for a straight line is y equals mx plus b, where x is the input, m is the slope of the line, b is the y-intercept, and y is the value of the line at that position, x. The values we have available to us to adjust or train are just m and b, where the m is that slope and b is the y-intercept. There's no other way to affect the position of the line, since the only other variables are x, our input, and y, our output. In machine learning, there are many m's, since there may be many features. The collection of these values is usually formed into a matrix that is denoted W for the weights matrix. Similarly for B, we arrange them together, and that's called the biases. The training process involves initializing some random values for W and B and attempting to predict the outputs with those values. As you might imagine, it does pretty poorly at first. But we can compare our model's predictions with the output that it should have produced and adjust the values in W and B such that we will have more accurate predictions on the next time around. So this process then repeats. Each iteration or cycle of updating the weights and biases is called one training step. So let's look at what that means more concretely for our data set. When we first start the training, it's like we drew a random line through the data. Then as each step of the training progresses, the line moves step by step closer to the ideal separation of the wine and beer. Once training is complete, it's time to see if the model is any good, using evaluation. This is where that data set that we set aside earlier comes into play. Evaluation allows us to test our model against data that has never been used for training. This metric allows us to see how the model might perform against data that has not yet seen. This is meant to be representative of how the model might perform in the real world. A good rule of thumb I use for a training evaluation split is somewhere on the order of 80-20 or 70-30. Much of this depends on the size of the original source dataset. If you have a lot of data, perhaps you don't need as big of a fraction for the evaluation dataset. Once you've done evaluation, it's possible that you want to see if you can further improve your training in any way. We can do this by tuning some of our parameters. There were a few that we implicitly assumed when we did our training, and now is a good time to go back and test those assumptions, try their values. One example of a parameter we can tune is how many times we run through the training set during training. We can actually show the data multiple times. So by doing that, we will potentially lead to higher accuracies. Another parameter is learning rate. This defines how far we shift the line during each step, based on the information from the previous training step. These values all play a role in how accurate our model can become and how long the training takes. For more complex models, initial conditions can play a significant role as well in determining the outcome of training. Differences can be seen depending on whether a model starts off training with values initialized as zeros versus some distribution of values and what that distribution is. As you can see, there are many considerations at this phase of training, and it's important that you define what makes a model good enough for you. Otherwise, we might find ourselves tweaking parameters for a very long time. Now, these parameters are typically referred to as hyperparameters. The adjustment or tuning of these hyperparameters still remains a bit more of an art than a science, and it's an experimental process that heavily depends on the specifics of your dataset, model, and training process. Once you're happy with your training and hyperparameters, guided by the evaluation step, it's finally time to use your model to do something useful. Machine learning is using data to answer questions, so prediction or inference is that step where we finally get to answer some questions. This is the point of all of this work, where the value of machine learning is realized. We can finally use our model to predict whether a given drink is wine or beer, given its color and alcohol percentage. The power of machine learning is that we were able to determine this and how to differentiate between wine and beer using our model rather than using human judgment and manual rules. You can extrapolate the ideas presented today to other problem domains as well, where the same principles apply. Gathering data, preparing that data, choosing a model, training it and evaluating it, doing your hyperparameter tuning, and finally, prediction. If you're looking for more ways to play with training and parameters, check out the TensorFlow Playground. It's a complete...
And the tool that he's showing here is one that we are going to play with a few times over, and this is like a publicly available tool.
completely browser-based.
I am going to move forward here, though. What I'd like to do right now is I want to read this slide, and then we're going to do our break for 5 minutes, and you guys probably need one at this point. Let's just read it, and then we'll walk away for a few. Machine learning models are defined by the presence or absence of human influence on raw data. Whether a reward is offered, specific feedback is given, or labels are used. And let's leave ourselves with that thought, and I'll see you guys in 5 minutes. All right, we had our break, and we left with this slide here. And we're going to move on to this next section. One thing I am going to point out is I was looking ahead in the video or in the PowerPoint to see how many more videos there were. And I'm thinking I'm going to like refrain from playing any more videos, but I do ask that you guys try to watch all the videos in there because some of them are really good and really helpful. And I know a lot of it doesn't make sense right now. But our next little segment here is we're going to go through these 3 different types of machine learning models, basically exploring that weird graphic. I'm going to try to do this as quickly as possible. So bear with me here because there is a lot of material here. We have like 90 slides to go, right? But I assure you, it's not going to go take that long. All right. So as we break down machine learning and AI, we have these 3 categories of learning for AI models. So supervised, unsupervised, and reinforcement. And you see the general descriptions here, right? Supervised is where you tell it what it's learning. Unsupervised is it figures it out on its own. And then reinforcement, like training a dog, basically. Think of it like that. There is this video here that talks about
Hi everyone. In this
the differences between the two, and I am fast forwarding it through it, but you guys should watch it. That one comes from Intel, and it is pretty helpful. But it basically tells you what's here, and basically we have these 2 grand categories for training models. The one being the unsupervised learning, and that is where things aren't labeled, and the way that it figures out what's what is by basically clustering things together. So we'll talk about each one of these. And supervised tends to use classification and regression to do its work. One little thing that they point out here is like, okay, AI's impact on jobs, right? So there's this big perception it's going to come and steal all of our jobs. And I like this little closing phrase. This concern should probably be reframed, right? This has happened in society over and over again. Hey, when the robots rise, what's your job? Programming the robots and fixing the robots, right? So when they come in to take your factory job, now your job is working with them, right? Data privacy is a big thing. And because we need large amounts of data to train the models, what data are we sharing? Right. So this is kind of an interesting thought as well. Bias and discrimination. We talked about this one last week, or was it 2 weeks ago? And there's a lot of ethical issues around this, and there aren't necessarily any rules that AI must follow. And nobody is telling AI companies that they must follow certain rules. I thought it was a very interesting article I read this past week, though, that a couple of the AI companies, and I forget which one, Anthropic's Claude, Trump made a thing saying, hey, we don't want to use these guys anymore because they won't let us use the AI to basically become Skynet, which is to decide on its own to kill people. The owners of the AI company don't want to allow that. And then the people that create ChatGPT feel the same way. So the US government wants to convince them, hey, give us the model that allows the AI model to kill. We want to use that one. And so that's kind of a weird situation right now, but that's a for real story, by the way. So it's like Skynet's happening right in front of us. We also talk about the singularity, right? So we talk about Skynet, and that's kind of like the singularity thing. I would ask that you read, this link. This is actually a pretty deep read. It comes from MIT, and it talks about this issue. Like, if we do achieve singularity, what does that do to machine learning? AI already knows everything, and it's really smart, and it's smarter than us. What do we have left to teach it? It's kind of where that goes. So that's something you can explore on your own. So key takeaways from this section, all the steps of doing machine learning, which was reinforced in that video, breaking things into categories, right, etc. And there's still a bunch of issues. All right, so the reflections. Let's go into supervised learning now, and you can see how the slides, I'm going to try to move them as fast as I can. So these are the basic bullets for supervised learning. So let's get into it. All right, so this is a branch of machine learning in which data that is fed to the model is already labeled. This is a cat, this is a dog, right? We're telling it what it is, kind of like your mom and dad do when you're a kid. You point at the bird and they're like, no, honey, That's a doggy, not a birdie, right? But eventually you pick it up, right? But their parents are labeling it for you. Or but generally this is kind of interesting. If we're going to label our data, who's labeling it? Well, we are. The humans are labeling, like your parents are labeling an animal for you so you know what it is in the future. So this graphic is kind of neat, right? So like look on the left here, we have data that's being fed in and we're telling the model that it's a dog or it's a cat. Then when we take a raw image, raw data here and feed it into the model, it can figure out correctly which is which, right? Okay, two different major types of problems that we solve with supervised learning. One falls into classification. So basically, it's a way to put things into the right category, so to speak, right? So like, is this email spam or is it not spam? If it's not sure, what do you think it does? It lets the message go through, right? Typically. But if it knows that it's spam, how does it know that it's spam? Maybe somebody at your work said, oh, this is spam, and hit the little spam button. So it's getting labeled, right? And then everybody else that gets it might not have to open it. And then we have regression. And regression is like where we did like the height and weight data, and it forms a pattern, and you can see that it's correlated. That's regression. So in other words, so they use an example, determine the relationship between the number of rash driving cases to the number of road accident cases by a driver. So here's a really easy algorithm. The more times I drive my car, the more likely I am to end up in an accident. Right? Sure. I can't get in an accident if I never get in the car, So like driving, it raises your chance of being in an accident just in general. Classification problems fall into their own categories, and this is where like this stuff gets deep, because every branch that we follow in that graphic has its own little sub branch, and we can classify things several different ways. One way is binary classification. Don't worry about memorizing any of the stuff right now, by the way. You can always refer to the PowerPoint if you want to know it, but later on we'll learn this stuff more in depth. Multi-class classification, like if it fits in multiple categories, for example. Regression is like the thing we did with height and weight. Notice all the data points and notice how it kind of suggests a pattern, right? So that's kind of the point. Right, so that's what regression is. There's a bunch of different supervised learning algorithms, or kind of like preconceived models, if you will, that we can fall into. And yeah, we go through all of these in the machine learning class, by the way, each one at a time, and code for them and all that stuff. But you will learn about all of those different things. I'm going to go ahead and click this here just to get that first video running. I like that one because this is like that top video on the right is an example of how computer vision works. And whether you guys are aware of this or not, there's computer vision systems sitting at most of our major intersections these days. There's cameras, and then they run software on top of them, and they do analysis. And they can see what is a truck and what is a car and what's a motorcycle and whatever. Some things that they use it for, right? I'll let you guys just read those on your own. There is also a quick little video here on spam filters, which I am skipping over. Just challenges with this for sure. If you're labeling data in advance, well, you better label things correctly. What if somebody puts the wrong label on something? Notice computation time is very high for supervised learning because it's got to compare, right? And a lot of this stuff is very, very computing resource intensive. Of course, a lot of computing power, a lot of RAM, a lot of bandwidth, a lot of processing. If you have bad data in there, that slows things down. And then you have this, what we call pre-processing of data. That's like where you try to make it better before it goes in. And then if you feed it bad data, it's the last bullet, you can get bad results, right? So if I throw in a picture of a bird and I tell the algorithm it's a cat, well, now I got some problems, yeah, because it's not going to learn correctly. interesting thing is when we're trying to feed a large amount of data into a data set and we're labeling it. Okay, let's say I'm trying to train an AI to recognize what a butterfly is, and that's kind of the point of this. But all I have is one picture of a monarch, you know. So here's what we use. We use generative AI often to create what we call synthetic data. It'll take an image that exists, it'll take away the texture, take away the color, enhance certain things, rotate it, flip it, superimpose it, you know, put different colors on it, whatever, to give you like 20 different versions of it that of basically the same thing, but it's more data that it can learn from. So if I don't have enough real data, I can sometimes use AI to generate more versions of the real data that I have in different fashions, so it has a bigger data set to work with. It's kind of weird, right? But this is very common in training AI models, is this whole concept of synthetic data. And I know when I first learned about it, I'm like, you're kidding me. You're using AI to generate stuff to train AI. Okay, why? Because it's cumbersome to do it the other way. That's the why. We also get data that's not balanced. Like I have a whole bunch of data about dogs, but I have hardly anything about cats. So once again, I use Gen AI to help me balance that out, and you know, to fill in the gaps of where I don't have data. We also have this concept of what we call data denoising. Data, you know, like anomalies. We want to get rid of the stuff that's like just off. You know, the guy was like checking like wine and beer, and he was looking at the alcohol level and the color. Well, I do know some beers that are red, right? And I do know some beers that are also really high alcohol, like wine is, right? But one thing's for sure, if I took my, I don't know, super high alcohol content rum or something that's like 100 proof and fed it into that model, it would probably break it, you know, because it wouldn't be able to go off color, whatever. So that type of thing. We also have this, you know, data interpolation issue as well, where, okay, so for example, if I tend to see that a bunch of data points fall in a certain spot on the graph, I can probably guess that other correlated data points would be in the same ranges, and I can just have AI throw some data in there for me, you know, because that's in the beer category, that's in the wine category, that's pretty clear. It's not in the rum 151 category, for example, right? So it can interpolate data and kind of save us a little bit of thing. All right, so here's some tasks that you can do with generative AI. If you guys aren't already aware of these things, you can generate images and music and text and designs and all sorts of crazy stuff, right? I mean, just look at the AI generated videos I've been throwing into the course. Like I'm not sitting down and creating those. I just feed it the PowerPoint and say, make me a video. And I don't do the complicated, I do the simple ones usually, but oh my God, this is just a great job, you know? And there's all sorts of tools out there in all sorts of areas now. And then how does generative AI do these things? Well, based upon models. Like if I'm doing music generation and I train my model on the blues, and the blues uses a 1-4-5 chord progression, and almost all the blues use that chord progression, I can give it a key and it can generate a chord progression for me. That's the blues, you know, just for example, because it studied the model, you know, and I think that's pretty bizarre. All right, really quick little quiz. Blank learning is used whenever you want to predict a certain outcome from a given input. Supervised learning, right? Labeled information. Certain type of continuity in the output. Which type of problem is it? Regression or classification? Right. Regression is what we are doing in data analytics. Highly correlated data is basically a good way to look at it. Machine learning uses a large amount of data and algorithms to perform the task. True or false? Totally true. More data than you can imagine, and we still create algorithms for it. All right, so here's the key takeaways for that section, folks. Let's move on. Let's talk about unsupervised learning now. Here's all the bullets we're going to talk about. And it basically very similar to supervised learning in a way, except the data we're feeding in is not being labeled in advance. And this is like really the key differentiator between these two, right? It has to figure out on its own by looking at the information how the data fits with each other, and it basically self-discovers it. So really good solution for look at these, like exploratory data analysis, looking at a set of data from outer space. We don't know what to make of it. We'll let the algorithm look at it. Cross-selling, customer segmentation, or image recognition. Like, what is this an image of? I don't know. I've never seen that thing before. Maybe the algorithm's got it figured out already, right? If you compare like this graphic with the previous one we looked at, look at the data coming in. It's not pre-labeled. It's not like your mom and dad going, that's a dog, that's a cat. That's like throwing you out into the wild, having you encounter both, and you go like, yeah, those scary ones are over in that category, and those scary ones are over in that category. I've seen enough of them to know if it's in that category or that category. I don't know what to call them, but I know which category it fits into. Right? This is really kind of like weird. And, we're not telling it in advance, right? Two major categories of this, right? Transformations of data. So like we actually alter the data to process it. And then the clustering approach where we just kind of group similar things together. So to give you an example, if I have a spreadsheet that's got a bunch of different data columns, right? And we were doing this in data analytics. Like if I plot things on an XY graph, I just need 2 columns to do that. I add a third column and a fourth and a fifth and a sixth. Think of the bar chart, right? Different departments had different expenditures for each quarter. And that's really hard to kind of plot on a graph for multiple things together. But if I color code it, I can put it on the same XY and kind of superimpose them over each other so you can see how it sits, right? So there's ways I can layer it. But otherwise, when I get past 2 data points, I get past 2-dimensional artwork, and then it becomes really hard for humans to kind of represent it. And so often what we do with big data sets is sometimes we combine data points together to do what we call dimensionality reduction, which is combining data points into one data point and then plotting them so that we can see what they look like. And this is really kind of a weird thing. We'll learn a lot about that as we go forward, by the way. Right, clustering, here's an example. Here's a picture of a bunch of balls. I can look at any one of them and tell you what kind of ball it is, but if it's not labeled, the algorithm can still look at them and go, well, this one looks like that one looks like this one looks like that one, and group them together. So that's called clustering, right? So it finds things that are similar and puts them into similar categories. And then, they say here, applications for this include gene sequence analysis, market research, and object recognition, right? That makes sense. Here's some of the unsupervised learning algorithms we're going to learn about later. The ones that we probably will use the most are probably the top 2 when we get to the machine learning class, but you will learn about all of them. And actually, we do some stuff with PCA too. Here's ways in which these technologies are used, right? So, I find this really fascinating because I often check out the Google News feeds, right? I like that as a conglomerated news feed from many sources. It categorizes article on the same story from various online news outlets. So this is what I like about Google News is like a story's happening, and instead of going to one news source and looking at one point of view on it, I see it on the Google News feed, and then there's this little button where you can see like 10 different, 20 or 30 different newspapers all writing about the same story. And it's so interesting that they come up with completely different headlines, right? You read the one from like MSNBC and it says one thing, and you read the one from Fox News and it says a different thing. And then you go over to a European news feed and they say something completely different. Where's the truth? But Google knows that they're all related to the same story, So interesting. Computer vision, right? So like looking at how to recognize objects, right? We did the dog cat thing enough. And then looking for things that are unusual. So anomaly detection is kind of a thing. We use this in medical imaging. So if you do enough medical imaging, you see the same kind of problem over and over in patients. then it's indicating something, and you can, use that to diagnose problems for people. We create what we call personas. Personas are kind of like simulated versions of people we use to do like marketing and things like that. But we can build, for example, like I play the guitar, so I'll use that as an example a lot. Like if I'm always looking at guitar ads and I'm being monitored that I do that, it's like, well, hey, he looks at guitar ads, maybe he'd be interested in a guitar case or some guitar picks or guitar strings, that kind of thing. So it's like, hey, he's always buying guitars, you could use some supplies, right? Recommendation engines, another place where this is used a lot. This is really weird though, right? Because if you're training a data set and nothing is labeled, it's got a lot of learning to do before it gets to the point where it actually works, right? And so it takes a while. And this is kind of like the Sisyphus. You guys ever hear that Greek myth, right? Where his task is to push the boulder up to the top of the mountain, and every time he gets up to the top, it falls back down. He's got to push it back up again, and he has to do that for eternity because he was like bad somehow. But the fact that we're giving it unlabeled data does take a long time to get to like good results with unsupervised learning. So it does require a lot of computing power, more so than unsupervised or supervised learning as a general rule of thumb. But ultimately, some labeling has to happen, because if you want to get it to the point where it's accurately, calling at a dog or a cat, you don't want the machine learning algorithm to come up with its own word for dog. Ultimately it figured out it's a dog. Now we got to label it until it's a dog. Once again, Gen AI is used to kind of augment these things. And this is a really weird one, right? We learned about how we can use Gen AI to create synthetic data to train our models better, right? And then we have what we call GANs and VAEs, which basically allows the model to create something, right? So like, for example, I asked the AI to create a deep fake of President Trump, and then, most of us can look at a synthetic version of something and go, that's not real. That's a synthetic Donald Trump, right? Because he would never say that, or he doesn't really look quite like that, that kind of thing. And then these really advanced unsupervised models can get to the point where they generate something artificial, and then they have a separate algorithm that evaluates the artificial thing it just created to see if it's convincing enough to convince itself that it's not artificial, to the point, and that process keeps going until it generates something that looks as close to something it can't determine if it's fake or not. I know that's kind of a convoluted explanation, but that's kind of how it works. And they call this, I think, the generative adversarial network, right? Where it, like, you just created a fake, but its own algorithm figures out that it's a fake. So you try again, right? And it keeps doing it until it gets good enough where it convinces itself that it's real. It's like kind of talking yourself into something that isn't happening in a way. Anomaly detection, once again. So Gen AI models really can locate those like weird pieces of data that really kind of don't fit, and then try to look at data that hasn't been yet fit in and see how that would fit into the model. So one example, they use like finding fraudulent credit card transactions. So here's a great one, because this has happened to me. I don't know. I'm not like a big dollar store shopper. Like every once in a while I'll go in there and I'll buy like candy or something like that, or a balloon for a birthday, but I generally don't shop at the dollar store. And then all of a sudden my credit union stopped my debit card from working because there was a $400 transaction at Dollar General, followed by a $300 transaction, followed by a $200. I did get all my money back, by the way, but somebody had like skimmed my card number and then created a fake card and started shopping at Dollar General. And why $400? Because that's the credit limit of what they accept at $400. Or somebody figured out that was my spend limit on my debit card or something like that. This is a long time ago. But the credit union immediately recognized, it's like, A, you never shop at Dollar General, And when you do, it's like $3. Why is it like 400, 300? Okay, stop that right there. That's a really good example. That's an anomaly. Um, all right, data clustering, and this is really kind of weird. And it says, imagine a massive consumer behavior data set. It may include age, gender, history, browsing patterns, etc. Gen AI models can be used to find these patterns a whole lot quicker than we would otherwise. And this is one of those things, and this is a really challenging one. Like if you start experimenting with your free Gen AI engines and you start giving it large data sets and ask it to do stuff like what's on this slide, like, hey, find me a piece of data that's anomalous here, right? And it's going through like 100,000 entries. It's going to run for a couple of minutes and it's go, you know what? You just ran out of credits. You got to pay me money, right? And that's where they get you. But if you do pay money and get the unlimited versions, you can get some of this type of stuff back, right? So if you're like on the fence about paying for it, just keep those things in mind. On representation learning, so like when you're trying to find things that has similar things to what you're doing and you want to find something else that's like that, it really helps in that regard. And Gen AI can kind of go in there and figure it out for you, right? So your English teachers here at Gateway may or may not encourage this behavior, by the way, so just be mindful of that when you do homework for classes, where and how you use AI. All right, comparing the two, labeled data, unlabeled data. I mean, that's a real big thing. When stuff is labeled, right, it can look at past trends and go, dog, cat, I get it. Unsupervised has to basically experiment on its own. Computing power is a lot for this, but it's significantly more for unsupervised learning because it's like learning the way we do. Like if you were just picked up, taken to a different planet, dropped off in a forest and go, good luck. Try to find safe food, safe water, safe whatever. You'd have to experiment a lot and probably die 5 million times before you got it figured out, right? All right. Quick little quiz here. Okay, unsupervised is the one we're looking for there. Just reinforcing the concepts there really quickly, folks. We are on the home stretch. I think we'll make it through all the slides and you guys will be thankful if the day is done once I get there. There is another approach, right? So we have the labeled and unlabeled approach. It's training our models, but there's also this reinforcement learning that I was talking about before. These are the bullets we will discuss. And basically the graphical representation of how this works, right, is, you do something, you either succeed or you don't. If that way didn't work, you try again. If you try the same thing again and it fails, it's kind of like putting your hand in the fire. After a while, you get smart and you stop putting your hand in the fire, right? Hopefully, hopefully you get smart. Otherwise, we call that the Darwin thing, right? Where they kind of like phase you out of evolution because you were not smart enough to not do that. But this is kind of the model for it. So you do stuff, and either you get a positive or a negative reward. If you get a positive reward, you do it again. You get a negative reward, you probably won't. Right. So that's kind of the training strategy. Here's the little analogy they have, right? So here's a maze, a little bit of cheese in there, and there's a mouse trying to find it. And it's got to find the right way to get there. And you can see right now it's not very close to the cheese. So it's got to kind of figure out in its head, how do I get to that cheese? And then remember that pattern, because every day there's a new piece of cheese, right? And after a while, it'll figure out how to get there. The same way you figure out how to drive to the grocery store without your GPS, right? Eventually you figure out how to get there, even if you previously didn't know. All right, so these are kind of the keywords we use in this area in reinforcement learning. So some of these refer to this basically. Where are we currently in our problem is the state. Agent, right? Okay, in the rat example, it's the rat. The rat's the one trying to figure it out. And if we're running AI, it's our AI agent. maybe you can like make one of those replica things and then ask it to do like, some like complicated task. And eventually, that's your agent. The action it needs to take to make the right or wrong decision. What is it trying to achieve? It's trying to get to the cheese. That's our reward. So if it works, it gets the cheese. What's the punishment? It's hungry. Hunger is not good. Right? And the environment, of course, is something that we can control. I forget how long this video is, but this one's kind of amusing. So I think I'm going to run it for a little bit. It's only a minute. So watch your pap. So our agent in this one is the Pac-Man. And it randomly, so this isn't run by a human. It just like figures out eventually how to move around and stay away from the little things. Every once in a while, it gets stuck and doesn't know where to go. But eventually it gets smart and it figures out how to not only stay away from those things, but tease them a little bit, right? And then after a while, after it trains, and this is like a machine learning algorithm on here, it not only figures out how to stay away from those things, it figures out how to eat them and complete the level and move on, right? And think about it. When you play this game, that's kind of the process you go through. First time you do it, you last like 10 seconds, and then you keep doing it and you get better at it, right? So that's kind of the reinforcement. All right. There's aspects obviously to reinforcement learning, and one aspect is what we call Q learning. And notice like the Q stands for quality. So it's like basically like the thing that you tried last time, how good was that? Did it kind of work, or did it completely work, or did it not work at all? That kind of thing. And it's not like yes or no. There's a range of possibility. And so ideally you want the best possible results, but sometimes you get kind of okay results, and kind of okay is better than bad results. Right. So you'd rather follow a kind of okay result rather than a bad result. But anyhow, really by analyzing things and putting a quality level on it, it allows you to learn it in a much deeper way than, that there's a nuance. It's not just right or wrong. Maybe the rat will get smart and just climb over the wall. We don't know, right? Here's some real world. They wanted to mention real world. All right, we won't do that. Let's move on now, and now we're going to start talking about this concept of deep learning, and sticking here on purpose, right? So we got AI versus machine learning versus deep learning. And really what this is, these are all layers, by the way. AI is the overarching technology. Machine learning is the biggest subset, and deep learning is a subset of machine learning. And we're going to talk about all these bullets here. And notice it says a type of machine learning in which the model learns to perform classification tasks directly from images, text, or sound, right? It looks at those things directly. And I want you to think about how profound that is. It's one thing for me to explain something to you, and another thing for me to give you an image and have you look at that image and decipher it. So like deep learning is this deeper level of machine learning, and really it's all based upon neural networks, right? And we saw kind of brief images of these. And the reason we use the word deep is a lot of basic machine learning models will have a layer or two of neurons. A deep learning model will have many, many layers of neurons, kind of like our brains do. And the learning goes much deeper, and it's kind of self-reinforcing at the same time. And notice it says traditional neural networks, 2 or 3 layers. Deep networks can have hundreds of layers, right? All right. Based, it says loosely on how our neurons are behave in our brain, right? And remember, they did mathematical models of this back in the 40s. They can automatically extract features without input from the programmer. this is kind of interesting. So like I can give it an image and it can look at the image and break the image apart and go, it's green, it's big, it's this size, it's whatever. And it can figure out those features or data points on its own rather than being fed the data points, right? You see that nuance. And every neural network node is basically a machine learning algorithm. So a deep learning is basically a collection of machine learning algorithms, if you will, right? When your data sets are really, really large and you have multiple layers, this will process those large data sets better. All of our neural networks will have a combination of these layers. All of them will have an input layer and an output layer, and then somewhere in the middle are the neurons. And I want you to notice like some of the features, like you can have multiple input points, you know, different types of data. All the input nodes, all the nodes in the network are interconnected. You can go from any node to any node, whether or not the path is followed is a different thing. There's little algorithms that are based around each one of the pathways and neurons. This shows two hidden layers, so we don't see what happens here. We see the data going in and we see the data coming out, but we don't see what happens here. Deep learning will add significantly more hidden layers to the mix, right? All right, so let's look at this thing here. AI, overarching technology. Machine learning, the biggest subset of AI. Deep learning is a subset of machine learning, right? And ultimately, we're talking about deep learning here. It enables the software to train itself to perform tasks with vast amount of data. And I think that's really kind of profound when you start to think about it, right? It's that deep learning thing. Okay, regular old machine learning, they can take a picture of a guy, right? And it'll figure out, you know, the roundness of the face, distance between the eyes, the nose width, eye socket depth, cheekbone structure, yada, yada, yada. It'll come up with some sort of an algorithm, and then it'll figure out, oh, that's Mark, you know? And then deep learning will take that same algorithm and, you know, it might have, like, this looks like it's doing like a couple layers, and the deep learning will have millions, and I want you to look at millions of parameters being passed around. So you guys remember when we write functions in Python, right? Maybe you don't remember, maybe you do. But when you're writing a function in Python, we move data around the program by passing parameters and arguments around the program. When we start to write some of these neural networks, and when we talk about our AI models, they're measured in the number of parameters that move around the model. So the number of data points. Deep learning neural networks have millions of parameters. Some of our most modern AI agents, like, you know, like ChatGPT 5 and Gemini 3 or whatever, you know, model versions they're on, will have trillions upon trillions of parameters in those models. And those models need to be trained, right? And it takes time to train them. Fascinating stuff, really. All right, so comparison here, classical machine learning. All right, so with regular ML, we do what we call feature engineering. We figure out the features or the data points, right, that represent the face, you know, the size, the shape, how far apart your eyes are. You know, do you have a unibrow or two brows or no brows? I don't know, whatever. And it turns it all into data, right? And then we apply a classifier algorithm. We figure out, okay, this fits with that fits with this, and we classify it and we figure it out. You know, with deep learning, it's kind of, it doesn't skip that step. That's not fair to say. It doesn't necessarily use that approach. It's not that it's not an aspect, but if you give it enough information that's already labeled, and I use the example of, like, if you know, like, a music pattern, and you go to an AI engine and ask it to create a blues song for you, well, how does it do that? Well, it's just following a pattern that's already established. So if you give it enough labeled information, it will identify the stuff on its own. Kind of interesting, right? You know, without doing that. All right. So deep learning is really good for identification of things, and it says face recognition, text translation, voice recognition, driver systems, lane, blah blah blah, all that stuff. Self-driving vehicle knowing to slow down as it approaches a crosswalk, especially if there's people in it, hopefully. Or like if you take a counterfeit note and try to put it into an ATM as a deposit, like you went to the photocopier, made a copy of your $20 bill and printed 100 of them, that type of thing. Or how about a smartphone app that gives you translation of a foreign street sign? And these are deep learning applications for sure. And I like this slide because I think this says it pretty well. It says deep learning represents a conceptual shift in thinking from how do you make the best features to how do you guide the model towards discovering the best features on its own. So this is like some of the real power of our Gen AI engines comes from this deep learning level and the training that goes on those levels. And you can tell this guy's happy because we pretty much have made it through the slideshow now. Pretty amazing that we got through that many slides here. So folks, here's the bibliography slide here. I don't know if there's another. Yeah, there's another. And there we go. And that wraps that little